Making Middleboxes someone else's problem. Network processing as a cloud service. First, some background. What are Middleboxes? Modern enterprise networks almost universally deploy what the paper calls middlebox infrastructures: firewalls, intrusion detection systems, web caches, web proxies, application delivery controllers, data loss prevention systems, and more. On this slide, we have a Cisco ASA firewall, a Citrix NetScaler, and a Juniper IDP. To begin, let's first discuss the state of affairs as they exist today. To get an idea of the Middlebox landscape, the authors surveyed 57 enterprise network administrators and compiled a data set. They found that administrators were forced into large deployments with high capital and operating expenses, complex management requirements, and the need for over-provisioning to react to failure and overload scenarios. These factors parallel common arguments for traditional cloud computation. Now, this is a real problem. Middlebox infrastructure is complex to manage, and middleboxes themselves have specialized processing, so management tools vary from vendor to vendor. With each middlebox comes the additional cost of training administrators or hiring specialists. This drives up operating expenditure. Capital expenditure is also high. The average very large network, more than 100,000 hosts, contained almost 3,000 L3 routers and almost 2,000 total middleboxes, spending over $1 million in the past 5 years on middlebox deployments. The average very small network, less than 1,000 hosts, contained about 7 L3 routers and 10 middleboxes, spending roughly $50,000 over 5 years. Also, in the median case, hardware upgrades occur roughly every 4 years. Cloud services: servers, storage, email, office productivity software. Would it stand to reason that a middlebox deployment would also benefit? Could there be such a thing as a middlebox service provider? To accomplish this, the paper asserts that a middlebox service provider must satisfy 3 goals in order to be considered viable. The cloud service must be functionally equivalent to in-house enterprise middlebox infrastructure. Whatever can be done or is being done in the current environment must be achievable in the cloud. For instance, a firewall must drop or allow packets. An intrusion detection system must trigger alarms. The challenge here is that these services are network topology dependent. The boxes themselves are physically placed on path. A WAN optimizer must compress traffic before it leaves the enterprise access link. A VPN tunnel must be terminated at the edge of the network. The complexity of the service must also be kept low. One of the problems with traditional middlebox infrastructure is that it is difficult and expensive to manage. If a cloud solution does not solve this problem, it makes no business sense for an enterprise to even bother switching. Also, performance overhead must be minimal. Under a cloud-based middlebox regime, traffic would be forwarded outside of the network for middlebox policy application and then forwarded from the cloud back inside. This clearly has the potential for an increase in packet latency and network bandwidth consumption. Can this be done? The authors think yes, that the same arguments made for cloud computing hold true for cloud middleboxing: reduction of hardware costs, in-house infrastructure elimination, and equivalent resources at lower cost due to economies of scale. In the study, a majority of administrators cite misconfiguration as the most common cause of failure, and many others cite overload and physical or electrical problems. On average, administrators surveyed spend up to 5 hours per week dealing with middlebox failures. And there are multiple potential benefits to outsourcing middlebox processing. Cloud middleboxes remove the need for upgrades. Cloud middleboxes remove the need for monitoring and diagnostics. No SNMP data aggregation or analysis is necessary at the enterprise. The cloud provider can generate these detailed reports. Cloud Middleboxes remove unnecessary IP addressing, routing, etc. Administrators can focus on policies instead of hardware functionality. Many administrative duties typically done by in-house IT are offloaded to the cloud provider. Cloud Middleboxes allow usage to scale up and down as necessary, never having to over-provision resources. Cloud Middleboxes are not restricted to enterprise customers the way hardware Middleboxes are. Like cloud computing services, Middlebox services can be offered to smaller organizations or home users. The authors have proposed a new Middlebox architecture. They call this APLOM, or the Appliance for Outsourcing Middleboxes. To start simply, consider an in-house Middlebox on a direct IP path between endpoints. The in-house Middlebox introduces only negligible processing latency, as traffic simply flows through it. The challenge is moving the Middlebox out of that path to the cloud, and having traffic bidirectionally continue to traverse it, without introducing noticeable path latency. Now, 3 questions arise from this need. Which Middleboxes can this be done for? What kind of redirection architecture is necessary to make it work? And what kind of cloud provider footprint will be necessary to minimize latency? At a minimum, there needs to be a generic device within the enterprise network which redirects traffic into the cloud. The options for redirection are bounce redirection, which is the simplest case. Traffic is redirected to the cloud's access point, processed by Middleboxes, and then sent back to the enterprise. This is simple, but it increases network latency. However, if the cloud provider has a large enough presence, like has an access point geographically local to the enterprise, this is feasible. Only the APLOM gateway needs to be cloud aware. Cloud processing is transparent to the end hosts. Another way is IP redirection. Internet users accessing enterprise resources are directed to the cloud first, and then tunneled to the enterprise. The cloud provider would announce an IP prefix on the enterprise's behalf, and hosts communicating with those IPs would be directed to the cloud provider. In practice, multiple cloud access points may be utilized for both ingress and egress traffic. A third way is DNS redirection. For multiple cloud access points, DNS redirection can be used, and is similar to that already used by CDNs. Inbound and outbound traffic is directed to internal or global DNS entries shared with the cloud provider. The challenge here is dealing with legacy applications which use IP addresses rather than DNS. And despite this challenge, the authors have chosen DNS redirection for their Middlebox cloud service design, utilizing Amazon Web Services for access points. To decrease the potential for latency, they have included a smart element, in that instead of using the closest cloud access point for each enterprise site, they choose the optimal access point for each enterprise site/cloud site client pair. So if you're accessing the enterprise from your home, the optimal access point is the cloud site between your home and the enterprise site, even if that access point does not happen to be physically closest to the enterprise site itself. With this method, the researchers were able to have 0 or negative latency inflation for 90% of traffic, and less than 10 milliseconds for the remaining 10%. It is worth noting that the provider footprint, i.e. how many access points it has available, does impact latency. For minimal latency for a nationwide client base, an Akamai-like footprint would be necessary. Additionally, the authors have evaluated a more advanced version of their APLOM Plus, which includes the compression capabilities of a typical WAN optimizing device. APLOM architecture consists of 3 components. 1, the gateway to redirect enterprise traffic. 2, corresponding functions and Middlebox capabilities at the cloud provider. And 3, a control plane responsible for managing and configuring cloud-based Middlebox components. Initially, enterprise customers must register IP addresses and hand over control of DNS to the cloud provider. Intrasite enterprise traffic can traverse the cloud infrastructure by using public IP addresses and private IP address manifests known to the cloud providers and Applum devices. With this information, the Applum gateway, co-located with the enterprise gateway router at the edge of the enterprise network, can perform its two primary functions: maintaining persistent tunnels to multiple cloud access points and directing outgoing traffic to whichever access point is appropriate. Traditional load balancing techniques are used to balance traffic across multiple Applum gateways. For the cloud provider, associating public IPs, enterprise customer IPs, and internal IPs is just the first step. Following that, traffic needs to be tunneled to and from customer sites, and Middlebox policies need to be applied to the customer's traffic. Core components at the cloud provider are tunnel endpoints to encapsulate, decapsulate, encrypt, decrypt, and compress, decompress customer traffic, Middlebox instances to process customer traffic, NAT translation services to translate between public and private IP addresses, and policy switching logic to steer packets between the above components. These architectural components already exist. The authors use software-based Middleboxes on an existing cloud infrastructure, AWS. In order to reduce administrative overhead and improve fault tolerance, the Applum architecture implements a control plane functionality in the form of a cloud controller, which manages network state associated with Applum gateways, access points, Middlebox instances, and tunnel endpoints. For each device, it sends out a periodic heartbeat health checks, gathers RTT and utilization statistics, and responds accordingly, optimizing redirection, launching additional instances, and enforcing pre-configured Middlebox policies. The control plane has three primary functions: redirection and optimization. Using measurement data from the cloud access points, the cloud controller pushes the current best tunnel selection strategies to the Applum gateways at the enterprise and mappings in the DNS. These are periodically updated based on the latest measurements. Policy configuration. Enterprise and Middlebox specific policies are implemented via the cloud controller. A programmable interface is accessed by administrators who specify policy chains of Middlebox processing, shaping traffic flow by specifying IP, port, and protocol rules for inbound and outbound traffic on each Middlebox. For instance, all inbound traffic must hit the firewall and then the intrusion detection system before being routed to its final destination inside the network. Middlebox scaling. As utilization increases on a particular Middlebox, the Applum provider simply increases the number of instances of that Middlebox. Using data from heartbeat health checks on all Middleboxes, the cloud controller detects changes in utilization. When utilization is high, the controller launches new Middleboxes and updates the policy switching framework. When utilization is low, the controller deactivates excess instances. Scaling is simpler if all Middlebox processing is performed in software on standard virtual machines, though with hardware, this can be achieved with policy switching alone. Built with off-the-shelf components running on existing cloud systems, the cloud controller runs on a home server running MySQL database to store policy data and statistics used in scaling Middlebox instances. On startup, the Applum software contacts the cloud controller and registers itself, fetches remote tunnel endpoints for each cloud access point, and requests a set of initial tunnel redirection mappings. A simple tunnel selection layer populated by the cloud controller directs traffic to the appropriate endpoint tunnel, and a redundancy elimination encoding module compresses all outgoing traffic. When run on a software router, ingress traffic comes from an attached host for whom the router serves as their default gateway. Running on a laptop or end host, static routes in the kernel direct application traffic to the appropriate egress VPN tunnel. EC2 data centers host tunnel endpoints, redundancy elimination decoders, Middlebox routers, and NATs, each with an inter-device switching layer and controller registration and monitoring service. For tunneling, the authors used OpenVPN. And for Middlebox processing, they use Viata, which performs firewalling, intrusion detection, caching, and application layer web filtering. Evaluation. For their evaluation, the authors measured HTTP load times, BitTorrent downloads, and voice over IP jitter. On the whole, they found that pages loaded more quickly, BitTorrent took slightly longer, and voice over IP latency variance had just a negligible increase. For scaling and failover, they tested a massive workload to force instance multiplication. The workload included streaming video and downloading large files simultaneously via HTTP and BitTorrent. New Middlebox instances were allocated and initialized in less than 100 milliseconds. Because the cloud controller checks for instance reachability every second, fault detection and failover is near instantaneous. In the lower image, we can see how instances scale with the degree of network load. Conclusions. A typical enterprise can outsource roughly 60% of its Middleboxes. The remaining 40% are largely composed of firewalls, but as the other IT infrastructure moves to the cloud, on-path firewalls will likely move with it. Through this study, the authors also found that a typical redirected packet experiences only 1.13 milliseconds of latency inflation. And with Applum Plus, the median case of bandwidth inflation was only 3.8%. In the worst case, it was only 8.1%. This is, on the whole, very minimal, and we begin to see that the costs may just outweigh the price. Discussion. Though user-facing devices like laptops, tablets, and printers will remain within the enterprise, businesses and governments are beginning to adopt a cloud-first approach to servers and services. Outsourcing Middleboxes is a logical next step in this process. Applum reduces the cost of Middlebox infrastructure with negligible latency or bandwidth increases. Unfortunately, typically tunneling traffic to a cloud provider necessitates paying for bandwidth twice, once for the enterprise network's access link, and again at the cloud provider. Additionally, cloud providers are mostly pricing bandwidth by volume. A dedicated Applum service provider would be able to take advantage of wholesale bandwidth, which is priced by transfer rate. However, cloud pricing structures like Amazon Direct Connect are already beginning to cater to an always-on hybrid data center model. VMware Cloud is also doing this. The costs are minimal compared to maintaining an in-house Middlebox infrastructure. One final concern is security, however. Cloud-based Middleboxes face the same skepticism as traditional cloud-based services. Though Applum encrypts traffic and isolates client VMs, industries like finance and healthcare, which have been reluctant to adopt cloud infrastructure, will likely remain reluctant. So, on a personal note, I'd like to say that some Middlebox functionality can already be exported to VMs, including firewalls, load balancers, web proxies, web caches, and application delivery controllers. Some of these are even being put in the cloud. CDNs are web caches, and static content is easy to serve from there. Citrix NetScalers can function as load balancers, web proxies, app firewalls, app gateways, routers, HTTP responders, cloud bridge connectors, and much more. Virtual appliance versions of these hardware devices are easy to place in front of the servers they're assisting and protecting, and that includes in the cloud. NetScalers can, for the most part, function as a Middlebox controller and Applum Plus device, as they can sit at the edge of the network and talk to other NetScalers and cloud services at the cloud access point using MPLS and broadband paths. Of course, the always-on functionality of the author's design is not built into these, but every day Amazon, VMware, and other service providers are expanding their hybrid cloud solutions to allow permanent cloud extensions of enterprise data centers. The paper is now more than 3 years old. We're halfway through 2015, more than halfway through, and this is happening. It's happening right now.